Hey, good to see you guys. Welcome back to your favorite pre-calculus class. This is section 4.1, polynomial functions and models. We're going to identify polynomial functions, graph them, identify zeros, talk about those zeros, analyze graphs based on end behavior. So let's start off here talking about a polynomial function. This right here's your definition of a polynomial function. Notice that you got a subscript n minus 1, and so on. Those are called your coefficients. And then your degrees here to the nth power, to the nth minus 1, and so on, those have to be an integer. No negative integers there, so just greater than or equal to 0 in your degrees. So let's look at some. I think it's best to kind of see some examples of polynomial functions. Okay, so let's look at this next examples here. So you got this first one. Are these polynomial functions? If so, state the degree and then write them in standard form. So your first one, notice it goes down by degree. It's x to the third, then minus 1/4 x squared, minus 9, and so on. So it's in the standard form. Is it a polynomial functions? Well, what you want to look at is, are these positive integers greater than or equal to 0? And it looks like all of them are, so no problems there. And your coefficients are all real numbers there. Okay, so this, yes, is a polynomial function, and it's of degree 3 there. B, is this one a polynomial function? It's also a polynomial function, but you want to write that as negative 3x to the fourth. You got to put this in standard form, so it's in descending order of degree there. So it's a fourth degree polynomial. And by the way, I should say on this first one here, third degree, that's also referred to as a cubic polynomial. Okay. C, now C is not. If you were to write this in exponential form, it would be y equals x to the 1/2. That's the same thing as square root of x, x to the 1/2. You cannot have rational exponents, so that one is not a polynomial function. This one also is not. You can't have, this is a polynomial over another polynomial, so you can't be dividing polynomials, so this one's a no as well. That's specifically referred to as a rational function, but it is not a polynomial function. You can't be dividing them there. E is, it is actually a polynomial function, y equals 8. There's no x on here, but they don't write this. It's just like x to the 0. So at the degree of 0, anything to the 0 power, if you remember, is 1. So this is just like y equals 8 times 1. So it's a 0th degree polynomial. So you can have y equals a constant. This one here, the end one, is also a polynomial function. If you were to, you might want to think about expanding this to see it. So you've got negative 2x to the third, then you expand this. You got x squared minus 2x plus 1, and then you'd expand that. So that becomes negative 2x to the fifth plus 4x to the fourth minus 2x to the third. Oops. Go away. Go away. There we go. So it's a fifth degree polynomial. Okay, so yes, that is a polynomial. Let's move to the next one here. These are just showing you some examples and some specific famous, if you will, polynomial functions. So y equals 0 is the 0 function. You got the constant function, that's a 0 degree, so that's like that y equals 8. Again, they don't write the x to the 0 on that. That's just, 8 times 1, so it's a 0. That's a constant function. Next one, now you've got first degree, so this is a linear function. Linear function, for example, 2x plus 4, right? This is to a first power, so it's a linear function. And then you've got the second degree, a quadratic. An example of that might be negative 3x squared plus 2x minus 4. That would be a quadratic or a second degree polynomial. All right, so graphs of polynomial functions are going to be smooth and continuous. So all polynomial functions, if they fit that definition, are smooth and continuous. You're not going to have a corner or a cusp, a gap, a hole. None of those are going to occur. And another way to think about this, whenever I draw a polynomial function, whatever a polynomial function looks like, I do not lift my pencil when I draw it, and it's nice and smooth. Okay, here's a polynomial function specifically called a power function. So like something maybe 2x to the fourth or something like that, a power function. So if you fit that mold. And the point in showing these slides here is if you increase the degree, if it's an even degree, it's going to look a lot like y equals x squared in black here. But if you increase that, so let's take it x to the fourth, you notice how it starts off a little slower, but after it passes through 1, 1, it takes off and it increases a little more rapidly. Or even if you compare x to the fourth in black over here compared to x to the eighth, again, it starts off a little slower, and then it increases more rapidly after that 1, 1. If you look at an odd function like x to the third, so here's the classic odd function x to the third. If you increase it to another odd function like x to the fifth there in blue, again, it kind of increases a little slower until it hits that 1, 1, then it takes off and it increases more rapidly for the odd functions there. Now, if you're thinking about transformations, you want to put this thing in standard form and think about it in this way. So you got negative x to the fifth. You know that part's going to reflect it about your x-axis. So you've taken, here's your x to the third originally, you flip it over the x-axis, so here's your negative x to the fifth, and then that plus 1 part of it will just bump it up 1. So now it's bumped up 1. So there's your negative x to the fifth, you just bump that thing up 1. Okay. So if you're thinking about this one right here, you've got 1/2 x minus 1 to the fourth. So this one looks a lot like x to the fourth, and x to the fourth is going to look a lot like x squared. Again, it just kind of starts off a little slower, then it increases a little more rapidly. So there's your x to the fourth. And what are you going to do with that? Well, we're going to have this 1/2 out front. So that's going to vertically shrink that thing. Okay, so it's a little flatter. And then that minus 1 inside that composition piece right there, that's just going to move it over 1. So then you're like that. Okay, so this is showing your shift over and then your compression by a factor of 1/2 there. Okay. So this is just showing our intercepts. You've got all these intercepts on a polynomial function potentially, and here's your y-intercept down there. Okay, we're going to look into our intercepts and our more specifically our x-intercepts, which are called 0. So if f of r equals 0, then r is your real 0. So you've got the following statements that are all similar. Okay, if r is a real 0 of a polynomial function, so let me take, for instance, I don't know, let me take this right here. See how you have the 0, 2. 2 is a 0, right? This is your x-intercept. So 2 is a real 0, or an x-intercept. It's also referred to as a solution. So zeros, x-intercepts, solutions, all the same thing there. Well, if 2 is a 0, then x minus r would be a factor. This is the equation x minus 2. Notice I took x squared and just moved it right 2. And you see how x minus 2 is a factor of this? X minus 2 is x minus 2. Right? X minus 2. If 2 is a 0, x minus 2 is a factor. Here's another one. Let's say I have, I don't know, I'll take negative 3. Right? Well, if negative 3 is a 0, then x minus negative 3 is a factor. And there's actually 2 of these. This is x plus 3 squared. Right, x plus 3 would be a factor of this thing. So whatever the r is, x minus that number is a factor. And of course it's a solution. So zeros, x-intercepts, solutions, all related there, all interchangeable. Alright, so let's look at this polynomial function. You got x plus 1 quantity squared times x minus 1. Find the x and y intercepts of the graph of f. So let's find our x-intercepts by letting y be 0 first. We've got x plus 1 squared, so we got 2 of these times x minus 2. Okay, so take each factor, say it equals 0, so x equals negative 1. I got another x equals negative 1, and then I got x equals 2. Oops, negative 1, sorry about that. Negative 1, and 2. Okay. Now we're going to use the intercepts to find the intervals on which the graph of f is above the x-axis and the intervals on which it's below. Then we'll kind of look at the look at the graph overall. Okay, so we found our x-intercepts. Let's go ahead and throw those on, our zeros. So I got -1, I hit, -1. Oh, come on. There we go. And I've got 2, I also hit 2. Now notice that there's 2 of these. So in math, what happens is if you've got, this is called with multiplicity, if you've got repeated zeros, what you say is x equals -2 with multiplicity of 2. That just means there's 2 of them. If there's an even amount, what's happening on the graph is it's just going to touch. So it'll just touch there, and I don't know if it's just going to touch there from the top side or from the bottom side, but it's just going to touch. Whereas this 0, x equals 2, there's only one of them. So if there's an odd amount, what the graph is going to do is it's going to cross through. It'll cross through like that, either increasing or maybe it'll cross through that way, but that's if you have an odd amount. Okay, so an even amount, so if you have even multiplicity, it's going to just touch it. Odd amount is going to cross through. And then what else I'm going to look at here is this is not in standard form. You know, if I was to expand this thing, you got x plus 1, x plus 1, x minus 2. You know, this would be x squared plus 2x plus 1 times x minus 2. Anyways, we'll take this x through to all of them. X cubed plus 2x squared plus x. Take the minus 2 through to all of them. So minus 2x squared minus 4x minus 2, and this becomes, in standard form, x cubed, that's gone, minus 3x minus 2. So what we're going to notice about, what's interesting about polynomial functions is this first term, okay, of the polynomial function kind of indicates the end behavior of the function. So you notice that it's x cubed. So what this is saying is at the extremities, in other words, as x increases or decreases with magnitude, it will behave like x cubed. And you know how x cubed looks like this, right? So that means at the extremities, this thing is going to go up to the right and down to the left. So I'm just going to make some markings on this. I know this thing is also going to go down to the left and up to the right because it behaves like an odd function with a positive leading coefficient. The leading coefficient of this is 1, right? You don't see the 1, but there's a 1 there, so it's positive. So it's not like it's flipped over like negative x cubed, okay? So I'm kind of getting an idea of this graph. Now all I got to do is plot a few points on this thing. So if I throw in, sorry, I run out of room here. Let's throw in 0 and find our y-intercept on this. If I throw 0 in, it looks like I got 0 plus 1 is 1, 1 squared times 0 minus 2 is -2. So I got 1 times -2 is -2. So I got 0, -2 it hits. Let me throw in some other ones. I want to throw in some points to the left of the zeros. I want to throw in some points to the right of the zeros and in between the zeros. Okay, so let's throw in another one in between the zeros. So I got 1 plus 1 is 2, 2 squared 4, 4 times -1, -4, so I got 1 -4 as well. Oops, come on. 1 -4. I'm going to throw in, let's throw in -2 to the left of that 0. So -2, I've got -1, -1 squared 1, 1 times -4, -4, so -2, I got -4 right here. So it looks like this thing's going to come up, kind of hit like this, and likely come back up through. And again, I'm going to throw in some more points if I'm doing this. I just don't want to take a whole lot of time on this because I got the graph right here. So if you take a look at it, there's some points. Anyways, you're plotting some points in between and so on. But you notice it's going down to the left, up to the right. You've got your zeros on there with multiplicity 2, so you know it just touches right there. You've got this 0. There's only one of them. If there's an odd amount, it's going to cross through, and so on. Okay, that's what this is saying. If you've got even multiplicity, it just touches. Odd multiplicity, it's going to cross through there. Now, this is an important point with these polynomial functions. If your degree is, whatever your degree is, then you're going to have at most n-1 turning points. Okay, so for instance, a third degree, like a third degree polynomial, will have at most 3 minus 1 or 2 turning points. right? Like this, maybe this is some third degree polynomial, and you notice you're turning once, twice, just twice. It's going to have at most 2 turning points. If it's a fourth degree, at most you're going to have 3 turning points, okay? And then you can go the other way around. If you count the turning points, so if you have however many turning points, then the degree is at least 1 more than that, right? So this one, let's go back to this third degree. So these are like, okay, I got 2 turning points, 1, 2 turning points, right? In other words, how many local maxes or mins do you have? 2 of them here. So that means it's at least a third degree, right? If I got another one, I got whatever like this. I got 1 turning point, 2 turning point, 3 turning points, 4 turning points. It's at least a 5th degree. This is at least a 5th degree. Might be more than that, but it's at least a 5th degree. And you also notice this goes down and up, so it's also odd, you know, from end behavior. We'll talk more about end behavior. So let's look at these here. Which of these are polynomial functions? You say, well, this is not smooth, nor is it continuous. Look at the problem there. Not polynomial. This one's smooth and continuous. And so then you count the turning points. 1, 2. So it's at least a third degree. This is at least a third degree. This one's not a polynomial. You got the sharp edge here. This one is, you got 1, 2, 3 turning points. This is at least a 4th degree polynomial. So we mentioned a little bit about the end behavior, right? But you're going to resemble, your end behavior is going to resemble that power function right there in the beginning. So here's what you want to think about. These two are even functions. I always think about x squared. So anytime you have an even degree, x squared, second power, and your leading coefficient is positive, you're going to go up to the left and up to the right. Anytime you have an even degree, I always think of negative x squared. Here I have an even degree, but the leading coefficient is negative. You're going to go down to the left, down to the right. Again, we don't know what's going on in between. We don't care. We're just stating this in terms of the end behavior. Okay. Now, whereas with the odd functions, I'm always thinking about x cubed. So this one goes down to the left, up to the right. Whereas negative x cubed, we'll flip that over. I'm going to go up to the left, down to the right. So anytime I have an odd degree and a leading coefficient that's negative, I'm going to go up to the left, down to the right. I don't know what's going on in between until I find zeros and plot some points and things like that, but that I do know. And this is how you state it technically. You know, as x goes to the right, so this is saying as x goes to the right, as I follow this function to the right, my y, what's the y doing? Y is going up. So x is right, left, f of x is up, down. Right? This one right here is saying as your x is going to the left, y is going up. Right? See that? It's going up. As we follow that function to the left, y is going up there. Which of the graphs could be the graph of this one? This is a pretty good little question. First of all, look at the power function. You say, all right, it's even degree. It's even degree, and the leading coefficient's 1. So it acts like x squared. Even degree, leading coefficient positive. So I know this thing's got to go up to the left, up to the right, just like x squared does. So that one's out. Okay, so I'm left with A, B, C. Now what I'm going to think about is it's a 4th degree. So since it's a 4th degree, I go back to that a couple slides back where I take the degree and I go, well, that means that there's at most 3 turning points, 1 less than the degree. There's at most 3 turning points. Well, this one's got 1, 2, 3, 4, 5 turning points. That one's out, too many turning points. But A and B both have 3 turning points, so both of those are options. And then the last part, just think about throwing in, you know, we don't know A and B, but that's okay. If you throw 0 in, so here's a little trick, find your y-intercept. Throw 0 in for x. Well, that's gone, because you got 0 for x, that's gone, and you're left with negative 6. If you throw 0 in for x, You got negative 6. It's got to be this one right here because this one's above the x-axis, so that one's out. So B it is. Now, can you write a polynomial function if you've got a graph that's shown? So we can go backwards. What you want to do is you want to label your zeros first. So here's your first one, negative 2. You've got 2, it touches. So you know it's with even multiplicity. So with multiplicity 2, there's at least 2 of them. There actually might be 4 or 6. There's an even amount, but we're going to go with 2 because we're going to assume the smallest degree possible. The other 0 is right there at 0. X equals 0 is another one. And the other one's right there at x equals 2. Notice that both of those cross through. So there's an odd amount of those. So we're just going to assume there's one of each of those. And now we're going to build our function. So y equals, I'm going to leave a constant a right there. I don't know what this a is. I don't know if it's positive or negative right now. We'll talk about that, but I'm just going to create the factors since I have the 0. So x minus the first 0, negative 2. Because if r is a 0, x minus r is a factor. So if negative 2 is a 0, x minus negative 2 is a factor. Okay, so notice we have 2 of them because it's with multiplicity 2. So I've taken care of both of those. Now x equals 0. If 0 is a 0, x minus 0 is a factor. And if 2 is a 0, x minus 2 is a factor. And what we want to do is we want to multiply this all out. So I've got x plus 2 times x plus 2, x squared plus 4x plus 4. And I've got x times x minus 2. I'm going to distribute that x through. So I've got x squared minus 2x. And now what I'm going to do, let me bring it over here a little bit. I'm going to take this x squared to everybody, and then I'm going to take the negative 2x through to everybody. So I've got x to the 4th, and I've got plus 4x cubed plus 4x squared. I've got minus 2x cubed minus 8x squared minus 8x. Combine any like terms. So 4x cubed minus 2x cubed, 2x cubed. I've got 4x squared minus 8x squared minus 4x squared minus 8x. Okay, so we're at this point. The problem is I just don't know what this a is in front. So what we do is we just put a point in. So I'm going to pick that negative 1, 6 right there. I'm going to plug it in for my x and my y. So my y is 6. My negative 1 is my x. And we've got 1 minus 2 minus 4 plus 8. So negative 1 minus 4, negative 5 plus 8, 3. Divide 3 both sides, so it looks like our a is 2. So now I go back to this equation right here, and I just plug 2 in. I'm sorry, I ran out of room right here. Plug the 2 in and distribute the 2 through to everybody, and you'll end up with y equals 2x to the 4th plus 8x cubed plus 8x squared minus 4x. Oh shoot, I'm sorry. This one right here. Hee hee. Just kidding. That one right there. So I got 2x to the 4th plus 4x cubed because I'm distributing the 2 through. 4x cubed minus 8x squared, that's a minus 8x squared. So I did that one, and then I distribute the 2 through right there, minus 16x on the end. Gosh, sorry to make a mess of that. So that's the polynomial function. Use the zeros, create that function. Okay. You could do that. You can continue to do that with you can analyze them by the zeros, and then take a look at. So here's your, analyze it with your zeros. Think about your. So you got x equals a half, x equals negative a half, x equals -3 with multiplicity 2. Right, so we're just touching at that -3. We're just touching because I got even multiplicity. I'm hitting at 1/2. I'm hitting at -1/2. I'm going to cross through those one way or another. And then you're just plugging points in. And you also want to think about, if I was to distribute everything through, this will be an x squared. Those two will give me a 4x squared. When I multiply x squared times 4x squared, I got 4x to the 4th. So this ends up being 4x to the 4th plus a bunch of junk. So I know it's even, so it's like x squared. And it's positive. So just like x squared, even and positive in front, this will go up and up. And now I just got to fill in points by plotting some points. So here's the look at that. Notice it goes up, up, just touches at the -3, crossing through there, plug some points into the equation to get some other points, and you're on your way. Okay. Now, we don't spend a whole lot of time on this, but I think it's worth noting that anytime you're given data, right, and it looks like it's cubic in form, you can also put that in just like we did into decimals with your A, B, and C, just like this. And it'll spit out, once you've put the data in, it'll spit out your A, B, C, and D and tell you what use regression to find that model for you. Okay? Just kind of note. All right, thanks for listening. Sorry, so long on this one. Long section. Appreciate it. See you guys in class.